Welcome to the Master of the NEC podcast, the ultimate destination for anyone passionate about the electrical trade. Whether you're a seasoned electrician, an eager apprentice, or just someone who wants to dive deep into the world of electrical work, you've come to the right place. Join your host, Paul Abernathy, a true authority in the industry with over 38 years of trade experience, as he electrifies your mind with in-depth discussions, expert tips, and valuable insights that will keep you ahead of the curve. Each episode, Paul will illuminate the complexities of the trade, decode the National Electrical Code, and share the latest industry trends, all while empowering you to take your electrical career to the next level. So, gear up, plug in, and get ready to supercharge your knowledge, because with the Master of the NEC podcast, the power is in your hands. Now get ready, here is your host, Paul Abernathy.
What up, everybody? Welcome to another episode of Master the NEC podcast, where I talk about the National Electrical Code and all things electrically related. On today's episode, it's a special one because we're going to be talking about mastering Ampacity, the ultimate guide to understanding Table 316, as well as all those other little nuanced tables like 31015B11 or 31015C1. When it comes to learning ampacities of conductors in the other different aspects of it being temperature limitations, terminal limitations, and all that good stuff. So there's a lot of stuff we're going to try to unpack in today's episode. So hopefully you're enjoying this podcast on whatever platform you enjoy. But remember, you also can get our free mobile app. It is available over on our website. It's free. We don't bombard you with ads or marketing stuff. It's a free app. And it's a web-based app, so it's not on the App Store, not on Google Store or iPhone Store. It's only on our website. The link will be down in the description, but it's FastTrax, T-R-A-X, system.com, FastTraxSystem.com, and you can get our free mobile app. We're always adding things to it. You can get access to great blogs. We have dozens of blogs on all different topics, calculations and everything. And you can also listen to our podcasts on the mobile app as well. But there's other tools and calculators, and we're always adding stuff to it. So check it out. It's free. Just go to our website and pick it up. And we'd love to have you there in the old app family, if you will. All right. So today we're going to be digging into that. We're going to focus on conductors ampacity. We're going to be focused on, obviously, ampacities. We're dealing with 31016. That is the table when it comes to conductor ampacity. Now, a lot of people ask me, they say, Paul, you should say what code cycle you're on, and I typically do. Today's show is going to be based on the 2023 edition of the National Electrical Code. But just understand that depending on which code cycle you're on, the ampacity table may change, 31015 B16. It may be 31016 for whatever cycle you're in. But we're talking ampacity today, but everything else that we deal with, it's all going to be really based on the 2023 edition of the National Electrical Code. Now, with that said, the fundamentals do not change. So what we're talking about, the important things of the ambient temperature corrections and adjustment factors, terminals and terminal ratings and the ampacities in themselves, that hasn't changed. That's not going to change even with code cycle changes. That's really not. We're not changing the ampacity of conductors right now. We're not, most of the manufacturers of wire and cable are pretty content with where the ampacities are. So none of that's really changing. So just, again, don't stress out saying, I don't want to listen to that because they're talking 2023. If you're on the 2020, it's still going to be applicable to you. And also, I should mention before I get into this that if you really want a detailed video with explanations and examples, you may want to consider subscribing to FastTrax Tube. It's just the same as FastTrax System. It's just with tube on the end. So FastTrax, T-R-A-X, Tube, T-U-B-E.com. That's our video platform. And there's a lot of very tailored videos over there. It's not the garbage that you'll get by just randomly searching on YouTube. I guess I shouldn't say it's all garbage because I do have some videos up there and I don't consider that garbage. But you get more detailed, no commercial type of things over on our Fast Tracks tube. It's also available on fasttrackstv.com, by the way. All right, so that's what we're focusing on today, and we're talking about that. But by the end of this episode, you'll understand sizing conductors. You'll understand the NEC when it comes to ampacities and limitations based on the terminal ratings and temperature and all that kind of stuff. So we'll try to give you as much as we can in this episode so that your takeaway is that you're a little bit better than you were when you started, okay? Before you started this episode. That's our goal. That's what I'm trying to do anyway. All right, let's start off first and understand the structure when it comes to the ampacity tables 31016, which again, there's other ampacity tables, 31017, 31018, 31019, but the most common one used for 0 to 2000 volts applications, the primary ampacity table that you're going to use, especially if you're implementing adjustment and corrections to an ampacity value, is going to be 310.16, okay? Now, it's important that I tell you table 310.16 because there's obviously a section 310.16, which gives you some of the backbones that reminds you that it's based on 30 degrees Celsius, 86 degrees Fahrenheit. It's based on not more than 3 current carrying conductors. That's under the normal 310.16, not the table. Now, years ago, it was also incorporated into the table, but the way it is now, that's the code reference in the code, and then you go to the actual table to actually see the actual ampacities, okay? So I just want to make sure you understand that just because we say table 310.16, there is an actual 310.16 in the code that gives you a little more of the backbone behind it. And that is again, not more than 3, ambient temperature, 30 degrees Celsius, 86 degrees Fahrenheit, 0 to 2000 volts, all of that. It gives you that in the code so that you can adequately use table 310.16 properly, okay? Just want to make sure that we understand that before we get too deep into it. Now, 310.16, the table is broken down into aluminum on the left, aluminum on the right, copper on the left, and it's broken down into a 60, 75, and a 90-degree column. Now, the 60-degree column is used for 60-degree terminations limits. Okay, now this also is going to be applicable, for example, to non-metallic sheath cable. Under 334.80, it's going to say that, you know what, I'll let you, and we'll see later, I'll let you do adjustment and corrections from the 90-degree ampacity, but that's only for adjustment and corrective purposes, and that is when it's not 30 degrees Celsius or 86 degrees Fahrenheit, or it's more than 3 current carrying conductors, right? Then if it's that way, I'll let you use the 90 to do these adjustments or corrections. But ultimately, at the end of the day, my temperature limitation is still going to be, or my ampacity limit is still going to be in the 60-degree column. Just because we're going to let you do something, you're still going to be limited to 60 degrees C, okay? And that also is going to apply for 100 amps, for less than 100 amps, okay? So that's going to be 110.14C1A3, for example, is when we're dealing with the limitations when it comes to terminals and temperature, okay? So, and we'll cover all that, but I just want to kind of set the tone. The 60-degree column is, again, typically when you've got under 100 amp application, when you have a missing link, in other words, you don't know what the terminal rating is, but you know it's under 100 amps, then you're going to be defaulting to the 60-degree column, okay? Those type of things. We have a 75-degree, and that's the most common used for, again, 100 amps or more, but also you'll find that even if the conductor is, let's say, a smaller conductor like a 14 gauge THHN, that if the terminal is rated 75, if the insulation on the conductor is rated at least 75, and of course THHN would be at least 75, it's 90 dry, okay, then you're going to be able to use the 75, even though it's technically under 100 amperes, okay? So that's why it's so important to understand the nuances. Okay. Now, again, the caveat to that is if you had 14 or 12 inside of a non-metallic sheath cable, then that rule doesn't apply. It's still going to be limited to the 60, even though you could do adjustment and corrections from the 90. This is single insulated conductors. We're just talking just regular old THHN that you would pull in a raceway. Okay. If your terminals are rated 75, if your insulation on the conductor is rated at least 75, and if the terminal at the other end of whatever it's connecting to on the equipment is rated at least 75, even if the ampacity was less than 100, you still could use the 75-degree column. Why? Because everything is rated 75 or greater. That makes sense? So these are little nuances that you have to learn, and they can be very impactful because, if you're preparing for an electrical exam and it may give you everything in the equation to size a conductor, but it ultimately does not tell you the terminal rating. And if the ampacity is under 100, it doesn't matter if it's THHN. If the ampacity is under 100 and they didn't tell you what the terminals are rated at, then guess what? Because it's under 100, you're going to be locked in the 60-degree column as far as ampacity is concerned. Okay? So it's important to understand those nuances. And again, I'll remind you, we do have a great video called Derating Demystified over on Fast Track's Tube, if you're interested in that. And again, it's $99 a year. It's your way of saying thank you to us. It helps us continue to go, and it's, you help support the program. So we appreciate all of you that subscribe to that. Now, if you're in our Fast Tracks program and you purchase the enhanced program, then you already get 12 months. Our hope is that you'll renew it at the end of a year and keep that Fast Tracks Tube subscription because you find it is important. We're hoping that you do. Okay. And of course, you have the 90-degree column. Now, the 90-degree column is typically used for adjustment and correction purposes. Okay. However, it's important to realize that you could, in a real-world scenario, you could have a conductor insulation that's rated 90. You could have a terminal that's rated 90. And you could have a piece of equipment at the other end that has terminals on it that are rated 90. Guess what? If that's the case, then I can use the ampacity from the 90-degree column. Yeah. Because everything is rated 90. Now, again, just for clarity, that's not going to apply to non-metallic sheath cable because that only lets you use the ampacity under 90 to do adjustment and corrections, which ultimately it's not going to have more ampacity that's under the 60-degree column. Okay. Again, I understand there's going to be a large collection of people out there that even if I explain this in the first 12 minutes of this video or podcast, you're still not going to get it. And you're going to say, that was confusing. You know what? Haters are there anyway, so I can't do anything about it. All I can do is say, go back, re-listen to the first 12 minutes of this podcast, and then maybe go watch our Derating Demystified video. And it'll eventually, once it locks in, it'll lock in, okay? And you'll get it, okay? I'm doing my best here to try to convey it for you, but again, that's the concepts. Now, let's look at some basic uses of table 310/16s. Let's say you need a conductor that carries 50 amperes, and we're just going to go with what we have, okay? We're just going to take it at face value, the conversation. We're not talking right now about in the use in the field. That's the other thing that you have to remember if you're doing exam prep, is that a lot of times they'll ask you a question. Don't let your mind wander to what you would do in the field. Only answer the question they give you on the exam based on what they give you. Don't let your mind wander. Okay? So you're like, okay, even if you're thinking, even if I don't have all the details when I'm trying to answer a question on an exam, your mind starts going left and right, up, down, and stress starts getting built up, and it's like, calm down, relax. I'm going to give you some understandings here, okay? And we're going to give you what you're liable to really see in the real world here. So I have a THHN. It's 90 degrees C rated insulation. That's what the T. T stands for thermoplastic. The H's, if you had only one H in there, like THW, that would be 75. But since I have two H's, that's 90 in a dry location. And then you've got the N, which is nylon. So two H's, high heat. Just remember, high heat, that's 90. T, thermoplastic. And the N is a nylon, and that is just a covering that gets extruded over the insulation. And the nylon has absolutely zero insulating value. It's there to protect the insulation when you're pulling it in a raceway, and it reduces the coefficient of friction, so it makes it a little easier to pull in conjunction with pulling lubricant. Okay. It has no insulating value at all. So if you get some nylon that's scuffed up, scratched, or whatnot, unless it's an oil and gas environment, and when we say that, we mean if you're installing THHN in an oil and gas environment where it is a likelihood that it will come in contact with oil and gas because of the environment to where it's being installed, then the nylon can't be damaged. But anywhere else in 99% of your normal installations, it doesn't matter if the nylon gets eaten up during the installation. In fact, it served its purpose. It protected the insulation. But just don't misconstrue the nylon as actually being insulation, because it's not. It's just a covering. That's it. Okay, so in our case, let's say we need a conductor that carries 50 amps. We're going to be using THHN copper. And oh, by the way, for those that are on exams, if it doesn't say copper, you always assume copper. Don't ever let your mind wander to aluminum, even though the answers might give you an answer in aluminum. It's copper is always the first you go to unless they state otherwise, okay? In the real world, you choose whatever you want, okay? But in an exam, if they don't say the conductor material, then you just assume copper, okay? Here, I am giving you an assumption rule. Always assume copper unless they state otherwise, okay? So we have THHN, it's 90 degrees rated, but most equipment that you're going to find out there today is not going to have a terminal that is rated 90. Now, that's not to say Polaris splices, those lugs, okay, those type of thing, inline terminal blocks that you might find in that goes in wireways, they might be rated 90, but typically on equipment, they're not going to be rated 90. They're usually going to be 75 degrees C. Now, on occasions back in the day, you would see 60/75, but to be honest with you, if it says 60/75, then you can ignore the 60 and you'd use the 75. You get what I'm saying? So even though it's THHN and we know it's 90 degree rated insulation, okay, and we're not even talking about Ampacity tables right now. We're just talking conductor. It's 90 degrees C rated, but you're going to be limited because most of the terminations are going to be 75 degrees C. And again, in your panel, electrical panel, most all of those terminations on breakers are all going to be at least 75, okay? So that's why we're using real world scenarios here. Now, step one, we're going to use a 75 degree column. And you're thinking, wait a minute, Paul, it's 50 amperes. So 110.14, and do me a favor, pause the podcast, go look at 110.14c, and go down, and you're saying, okay, it says if it's under 100 amps, then I'm stuck on the 60. Why did Paul go to the 75? Well, the reason we did, because, again, the vast majority of your terminations are rated 75. Even though the temperature rating on the conductor is 90, we know that we can't use that 90 to start with. We're going to be limited to the 75 because of the terminals, okay? They're rated 75, whether it's at the breaker or whether it's at the piece of equipment, whatever. Okay, so we're going to use the 75. So let's look in the 75 degree column to find our ampacity first, okay? And we want to make sure that it is greater than or equal to 50 amperes. All right, so I've got my code book here. I'm going to go down to the code book, and I'm going to go down to 31016 and do it with me. If you want to get better and you're listening to this podcast, pause it and, take your time and go down and work through it. So you'll see that an 8 gauge copper under the 75 degree column is good for 50 amps. And you'll see that a 6 gauge is good for 65 amps. So in our case, the 8 AWG copper THHN is good for 50 amps. 50 amps. Now, that is only good, folks, under this column. It is only good if it is not more than 3 current carrying conductors. And again, this is why you got to go look at the actual 31016 to understand those limitations. Okay. Now, the good news is if you're using Link or you're studying with the NFPA document or you're in the NEC, then the 31016 is near the table, so it's they're right next to each other, so it's not brain surgery. But if you go look in the 2023 edition of the NEC, you're going to see 4 things there. You're going to see number 1, in order to be able to use 31016, the conductors are rated 0 volts through 2000 volts. That's number 1. Number 2, the conductors are rated either 60, 75, or 90. Check. Number 3, it says wiring is installed in a 30 degrees C, 86 degrees ambient temperature. Probably not what you've got, okay? But let's start out right now and say, yes, it's 30 degrees ambient Celsius or 86 degrees Fahrenheit, right? So we're good. And then it says the equipment is rated 75 degrees C. And so we know what our equipment rating is. And again, the vast majority of in the field, the equipment's going to be at least 75 degrees C, okay? Now, there's exceptions to every rule. There are lugs that may be rated 90. There may be lugs that are limited to 60. But again, I can't cover everything in a podcast. And there's always a hater out there that's going to say, well, he didn't say this, whatever. Then I eagerly encourage them to create their own podcast and do whatever the hell they want to do. But I got to do the best I can to keep it rolling. So we're going to go with 75 degree terminals. Okay. So into that scenario is in that perfect world, okay, 30 degrees Celsius, 86 degrees Fahrenheit, terminals rated 75 degrees C, and no more than 3 current carrying conductors in that raceway, then I'm going to say the 8 copper is good to go. It's good for 50 amps. We are good to go based on the criteria that we have so far. Okay. Now let's take this to another level. That's a perfect world scenario. Now, by the way, if the lugs were 60 degree rated, okay? Or I'm in a job site, I go to a job site, I can't tell what the lugs are rated at either end. How would I apply this to that? Same scenario. Even though it's THHN, it's 90 degrees C, I'm not going to assume the 75 degree conductor rating. The terminal rating. So I'm going to say, well, since I can't verify that in the real world, all I can look at and go, well, yes, the insulation of the conductor is over 75, but I have no idea what that terminal rating is. I can't tell. I can't see it. Or I may be able to see the breaker, but I can't tell by the equipment. Well, in that case, even though it's THHN, you're going to have to fall to the 60 degree column. Why? Because 110.14C1A tells us that. So in that case, if I'm locked into the 60 degree column because of a lack of information, then I got to go down and say, okay, I still got to cover that 55. So in that case, it would be a 6 gauge because that is good for 55 amps. So it can easily handle the 50, whereas an 8 gauge is only good for 40. You see what I'm saying? That's how you have to mentally think about it. And you've got to know all these pieces. Folks, I've told you this in many podcasts that one of the hardest things for people to grasp is ampacities and adjustment and corrections and how you would maneuver back and forth understanding ampacities. It's tough. It's not easy. And but it is easy to make a mistake. Okay? Okay, now let's go on to adjustment and corrections. Okay? And this is where a lot of people start to tumble along the side and it gets confusing for them. So let's start out with understanding some fundamentals. So what we're going to talk about is adjustments. Now, what is an adjustment? An adjustment is the number of current carrying conductors that you have in a raceway, in a cable bundled together, things like that. If you're going to have more than 3, more than 3, or let's say 4 or more, you're going to have to make an adjustment to the ampacity of that conductor. So it's not going to have the same ampacity that you started out with because there's going to be mutual heating. That means you've got other conductors, more than 3. It's obviously not optimal for 310/16. So you're going to have to modify the ampacity that's the baseline of this table in some way. And that's what we call an adjustment. So I could have 4 current carrying conductors in there. I could have 5 current carrying. I could have 6. I could have 10. All of those current carrying conductors over 3 are going to play a role on how much actual current that those conductors that are together in that raceway can carry or in that bundle of cable. It's going to have an impact on that. Now, where do we see that at? So if you're new to the code and maybe you're studying and your first time, then you're going to get familiar with 310.15. And 310.15 is kind of giving foundational information about bundling, about the number of current carrying conductors, all these type of things. So get familiar with it. But the first one we'll look at is 310.15c. Now, 310.15c is talking about, again, adjustments. And I'll read it to you from the code so that you understand it verbatim. It says 310.15c adjustment factor. C1, it says more than 3 current carrying conductors. So that is the trigger here. If it's not more than 3 current carrying conductors and the ambient temperature is still 30 degrees Celsius, 86 degrees Fahrenheit, then guess what? You just pull Ampacity straight from the table, happy, and you just go on your merry way. But if there is something in there that's going to require a trigger of an adjustment, you got to understand how to do it. And here's what the code says. It says the ampacity of each conductor shall be reduced as shown. Okay, so it's telling you right away, the ampacity baseline in 310.16 is going to get reduced based on the values that are given in a table. And that table is 310.15c1. And it says, where the number of current carrying conductors in a raceway or cable exceeds 3, or where single conductors or multi-conductor cables not installed in a raceway, that means they're cables like non-metallic sheath cables that are just, tie wrapped together in a big bundled mass, that type of thing, they're installed without maintaining spacing continuously in lengths longer than 24 inches. So basically anything over 24 inches, if they're not maintaining spacing, then they're bundled. And that's going to affect the ampacity of those conductors that are in those cables because the heat can't dissipate. It's locked in this bundle, right? So it's going to affect what the ampacity is of the conductors that are in that massive bundle. You get me? All right, now it says every current carrying conductor of a parallel set of conductors shall be counted as a current carrying conductor. Okay, so if I have a parallel set of 3 blacks, 3 reds, 3 blues, okay, then every one of those conductors are considered current carrying conductors. So if I have 3 sets, 3 blacks, 3 sets, then it's 3 blacks in a raceway, whatever, they would all be considered current carrying conductors, basically what you're saying, okay? Now, it goes on to say where the conductors of different systems are provided in 300.3 are installed in a common raceway or cable. It says the adjustment factor shown in 310.15c1 shall apply only to the number of power and lighting conductors. So that's a situation where you may have other conductors, let's say signaling and control, that actually have the equal insulation rating on it. Maybe it's the same insulation rating, 90 degrees C, as the power and lighting, but they're not power and lighting. So you don't count those as current carrying conductors, okay? You're only going to apply it to the power and lighting conductors because they're the ones that are going to generate significant heat, okay? So that's what it's saying, okay? So that's the basic. And of course, I will tell you that C1 also goes down and talks about what you have to do for cable trays. It reminds you of adjustment factors shall not apply to conductors in raceways that have a length not exceeding 24 inches. So if you have like what people call a nipple, and many people say, well, a nipple's 18 inches or a nipple's 24 inches. Get out of that mode. Really, go by what the code says. The code's not calling it a nipple here. It's just giving you a distance. So I could have a 24-inch or less raceway between 2 boxes. And yes, I might have a problem with raceway fill, but I don't have to apply adjustment factors that apply here when it's only 24 inches or less. Why? Because it's short enough that the heat's going to dissipate out of it. Now, you're still going to have raceway fill issues that you got to be aware of, and you could have an ambient temperature that you're going to have to do a correction for, but you just don't have to worry about the adjustment because it's such a small raceway, that type of thing. Okay? So I just wanted to point that out. Also, you have other things for underground conductors as they merge and leave from a trench. You got some relaxation for that. You also have relaxation for AC cable and MC cable. It's very strict caveats that you have to meet, whereas you can't. A cable overall can't have any PVC jacketing on it. It's just metal. Also, we're talking MC or AC, by the way. And then the cable is not more than 3 current conductors in each of the cables. The conductors inside of it are at 12 gauge and not a 14 or not a 10. They're all got to be 12. And then as long as your bundle is not more than 20 current carrying conductors that are stacked or supported on bridle rings that act like they're being bundled, as long as you're not exceeding 20 current carrying conductors collectively with all of the cables, then you don't have to apply this adjustment. So that can help you out in a commercial environment. Just got to know how many MC cables you're putting together so you don't bridge this, and you got to make sure that you meet all these caveats, and you can ignore this adjustment factor. Again, that's not removing the ambient correction. This is just an adjustment rule that you get to ignore. Now, if none of these apply, then, you still are going to have this. If any of these allowances don't apply, and you just have a raceway with conductors in it, and you exceed 3 current carrying conductors, then you're going to have to do an adjustment. And what is that going to fundamentally do? It's going to reduce the current carrying ability of that conductor. And if you put a lot of them in there, ultimately you can end up with a conductor that can't carry any current. And you think, well, it's still a conductor. It can obviously carry current. Yeah, but if the conductor is now compromised because you violate the code, and now it has mutual heating, it's a matter of time before that insulation will break down and fail. And then somebody like me comes along and gets hired as an expert witness, and then we find out you didn't follow the code. And then, of course, it may not be the reason the building burned down, but guess what? If we can tie it back to something you did wrong, insurances love that. And we as experts get paid good money to point the blame at other people. So just follow the code. Make it simple. Okay, so let's look at some example. Well, real quick, let's jump to the other. Let's cover these first, and then we'll give you some order of how you do these and how you would calculate these out, or things to think about. So that was the adjustment issue in 310.15c1. Now let's talk about the correction issue. This is where the ambient temperature that you're placing these conductors in are not in alignment with the general rules of 310.16. So I'm putting these conductors at this ampacity in an environment, in this raceway, in an ambient temperature that is other than 30 degrees Celsius and 86 degrees Fahrenheit, which is, be honest with you, probably inside of a building that's conditioned space. You don't worry about it that much when it comes to the ambient, because it's typically, it's not something you think too much about. You think more about the adjustment than you do the correction. Now, if I'm taking a raceway and I'm taking it through, let's say, a boiler room, or I'm taking it through an area where we have a actually known, documented, elevated ambient because of the environment that I'm going into, that's different, because that is going to have a direct impact on the ambient temperature as well as the annular temperature inside of the actual raceway itself. And so that's going to affect the ampacity of that conductor. Now, how does it affect it? Well, what we have to go look at now is 310.15b1. And when we look at 310.15b1, which is going to ultimately tell us that we're going to be looking at table 310.15b11 or 310.15b12. Now, again, this is for the 2023 edition of the NEC. Before it was just 310.15b1 and 310.15b2. They're the same thing, okay? It's just number changes, okay? So, again, if you're in an older edition, don't let it spook you. It's the same concept, same fundamentals. It's not, not anything more complicated than that. Now, one question I get from people is they ask me, Paul, what is the difference between 310.15b11 and 310.15b12? What's the difference? Well, you're going to be using 310.15b11 for 99.9999% of your applications, because that aligns itself with the 30 degrees C, 86 degree Fahrenheit baseline ampacities. You'll notice if you look at 310.15b12 that in the header of the text of the title of the table, you notice it says for ambient temperatures other than 40 degrees C. Whereas the 310.15b11 says 30 degrees C. That's because under table 310.16 for ampacity, remember I told you that it's based on the baseline of 30 degrees Celsius, 86 degrees Fahrenheit. So when we're adjusting, or in this case for the ambient temperature, we're correcting from the baseline ampacity, we're going to be doing it based on the value that's under the 30 degrees C baseline of 310.16. So you're saying, well, when would I use 310.15b12? Well, that is if you're using other tables, for example, like 310.18, 310.19, those type of tables, Well, if you're using those, then they're going to have a different ampacity value baseline on those ampacity tables. So if you were to take a second and just go look under the tables, for example, go look at 310.17. You'll notice that 310.17 is still based on 30 degrees C, 86 degrees Fahrenheit. So even 310.17, which is, again, single insulated conductors in free air, the ampacity is still going to use the correction table 310.15b11. But if you go down and look at 310.18, you'll notice, remember at the beginning, not in the table, but at the beginning, the charging statement, the 1, 2, 3, and 4, the caveats, if you will, you'll notice that it's based on 40 degrees C. Same thing with 310.19. It's based on 40 degrees C, which aligns itself with the ampacities of this table, align itself with the correction table 310.15b12. Does that make sense? That is something that many people, and there are some people out there that say, well, go on and take your pen or a marker and mark out 310.15b12. I would never tell you to do that because you just never know when an obscure question is going to come on an exam that you're going to need to use that table. And I would not want to do anything that's going to draw my attention away from it and think I never would use it. But for all of your in the field, all of your practical uses, you're going to be using 310.15b11, okay? And for you earlier cycle folks, it's 310.15b1. That's what you're going to be using when it comes to the correction due to ambient temperature, again, that's other than 30 degrees Celsius, 86 degrees Fahrenheit. Okay, now, let's talk a little bit about that table real quickly. So if you look at 310.15b11, you'll notice this table is broken down a little bit into, again, columns. You'll have the big column on the left that says ambient temperature, and you have a big column on the right that says ambient temperature. One is in Fahrenheit, one is in Celsius. Look, it's not complicated. We typically, conductors, it's whatever, on an exam, it's whichever you want to use. But in the real world, we typically stick to Fahrenheit because that's most of our thermometers, our temperature IR equipment, everything is pretty much given it to us in Fahrenheit. But it doesn't really matter because if you look at it, they're equivalent whether you go across the line from left to right. It doesn't matter. Now, one of the key takeaways that I want to talk about is look at the middle column where it says temperature ratings of conductor. Now, when you're applying this table, it's based on the modifier that you're going to use here is based on whatever the insulation is of the conductor. It's not based on the ampacity tables in 310.16, 60, 75. It's based on the conductor's insulation rating. Okay. So for example, if I'm doing THHN and I'm going to be doing an adjustment or correction because I have an elevated ambient temperature, and so I'm allowed to use the 90 degree ampacity to start my calculation, then when I come over here to find out what my multiplier is going to be, I'm going to be under the 90 degree column because that's what the insulation is on my conductor. You get me? So that's where people a lot of times will get lost. Now, if it was THWN, for example, and I was doing an application where it's in an environment, a wet location, it wasn't THWN-2, but it was just THWN, then it only has one H. So that means it's 75. So if I'm going to do a correction from an ambient temperature other than 30 degrees Celsius, 86 degrees Fahrenheit, and I end up having to find what my multiplier is, then when I come here, I'm going to be under the 75 degree column. I can't use the 90. Why? Because that insulation on that conductor is not rated 90 in that environment. It's only rated 75. So that's why I'm stuck to get my multiplier under the 75 degree column, depending on what the ambient temperature is based in Fahrenheit or Celsius. And that's why it's so important, folks, on an exam that you have a slide rule or a ruler or the edge of maybe your scratch paper to use to make sure that you go across. Because when you get into a stressful environment, you can forget, kind of get your lines messed up. And I want to make sure that you're moving across the tables accurately. So give you a straight edge or something with a straight line so you can make sure you're in the right column. So you have the right multiplier that you're going to be using, okay? Now, you'll notice that in the middle of this, you see that 1.00 for the 60, the 75, 90. That's right in the middle. If you go to the left, you'll notice how convenient that is 26 to 30 degrees Celsius. And if you go to the right, it's 78 to 86. So 86 being the max based on the ampacity of 31016. It's 30 degrees Celsius, 86 degrees Fahrenheit. That's why the multiplier is 1.00. So it's basically 1 for 1. Okay. There is nothing that changes if that's what you have. And if you had that, you didn't even need to go here. Okay. But it is right here. Okay. So anyway, that just kind of wanted to point that out so that everybody is really familiar. Also, if you look at the bottom, and I've had to explain this to people, what I told you earlier on which tables of ampacity go for which one of these, you'll notice there's a note at the bottom. And the note says that 31015B11 shall be used for tables 31016 and tables 31017. Okay. You notice that? So that should answer that, because again, I still get amazing amount of questions, but it's right there in the note. Yet I still get probably at least once or twice a week the question on this, on which table should I use, when it was right there in front of you. And if you fell into that trap, then you fall under reading comprehension issues. And that's why our Fast Tracks program is designed the way it is. It's a structured learning program that walks you through these things to make you think, because these aren't just exam stuff. This is real world, and you can get a conductor sized improperly very quickly. And so, again, I like to point out all these little things because it really helps you understand the nuances of the code. And these are notes. They're not informational notes. Okay, there's a difference. These notes, when you just see a note under a table, it is very much applicable, or I should say applies very much to the rule. Whereas if you see informational note, it doesn't apply. It's not enforceable. It's just good information. It's a learning tool. It maybe gives you some guidance. But when you see note under tables or notes used in the code under a section, it is very much still a code rule. In other words, these notes apply to the code. It's not optional. Okay? You get what I'm saying? Okay. All right, so let's think of the structure of how we would flow through this. Let's start with the order of matter. We start with the 90 degree C ampacity. That's what we would start with if the conductor is rated, the insulation is rated for 90. Okay, we start with this and go, okay, it's rated for 90. All right. And again, we're not adding any terminations in it right now. We'll let that be the last step. But first things first, we start with the 90 degree ampacity. Now we apply the modifiers, whether it's apply the adjustments if it's more than 3 current carrying conductors, or we apply the correction if the ambient temperature is that's greater than or less than 30 degrees Celsius, 86 degrees Fahrenheit. And then we select the conductor based on the 75 degree column due to the termination. Okay, so that's the easiest way to do it, because basically you just find the conductor under the 90, right? And then multiply by the modifiers. So it would be 90 times whatever it would be, 0.70 for the adjustment, and then another 0.70, let's say, for the correction, depending on which one you're using from the tables. And then you're going to get an end ampacity. That end ampacity is what you're going to look under the 75 degree column and make sure, one, you've got a conductor that can handle the load. That's important. Okay. And that you're not going to have a load that exceeds the new calculated ampacity, but also you're not exceeding the limitations under the 75 degree column, because that was the terminals. They're limited to that. And this just keeps it simple. Now, one other way you could do it is you could actually look at what load you have, and you say, look, I got to have this load. Okay, this is my load. This is my amps. This is what I need. Now, I need to see what size conductor I need to have based on the fact that I've got adjustment and corrections. So you start with your load that you have to have, say 50 amps. And then you use division. And you go 50 amps divided by 0.70 divided by 0.70, and that's going to give you an ampacity value. Then you take that, and then you go to the 90 degree column, and you find a conductor that has equal to or greater than that ampacity that you just did. And then once you find that, you can check your math by now using multiplication and go the other way. And it should be greater than or equal to the ampacity that you need. It should be more, okay, or equal to. So there's two different ways to do it. Now, if that is confusing for you, do me a favor, because again, podcasts can be confusing, and there's just different two ways to approach this. In the real world, I say keep it simple. Unless you're dealing with non-metallic sheath cable, if you're just dealing with conductors and raceways, THHNs and things like that, then automatically, whatever load you need, go to the 90. If you know you've got adjustment and corrections, go to the 90. And then once you're there, then you can apply your modifiers. Multiply it by whatever it comes from table 31015 B11, and then multiply again by whatever you get 31015 C1, and that's going to be that's your new ampacity. Okay? Now, you just go to the 75-degree column and pick a conductor that equals or greater than that ampacity. And you're done. Because you really can't screw it up from there. Okay? So anyway, that's the basis for it. Now, if you're dealing with non-metallic sheath cable, for example, you're locked into the 60. So even if you're going to choose the 90-degree ampacity and do adjustment and corrections from that, and now you're going to have this miraculous new ampacity, you're still going to go to the columns. You're going to still go to the 60-degree column and pick the conductor that you need to handle your load. You're just hoping that after adjustment and correction, that conductor is equal to or greater than what load you need to handle under column 6, under the 60-degree column. Even though it may come back as 10 amps higher than the 60-degree column, it doesn't matter. You don't get to use those extra 10 amps. You're just validating that your conductor is still good under the 60-degree when you're dealing with non-metallic sheath cable. Okay? And again, if that confuses you, and again, podcasts, and people say, well, I can explain it much better. Well, you do that. Okay? It is a podcast, by the way. So I got to paint you that mental picture. But again, go watch Derating Demystified if that confuses you, and you'll get it. Once you get it, folks, you'll get it. Okay? All right. Let's look at an example of a classic question and see if we can't answer this question, because there's other things that we have to think about. What about current carrying conductors? What about if they're continuous loads? What is a continuous load? Well, the interesting thing about the National Electrical Code is it gives you a definition of a continuous load, and that is any load at maximum output for 3 hours or more. So a range, for example, is never going to be a continuous load because the loads always cycle. It's never going to be at its maximum output, and we would never take a range, for example, as a continuous load. Even though you say, well, on Thanksgiving, I'm going to cook a turkey for 4 hours, isn't that the range is on continuously for 4 hours? Yes, but it's never at its maximum output. It's thermostatically controlled. It's never going to be. It's cutting on, cutting off to maintain a certain temperature. Okay? So it doesn't meet the definition of a continuous load. Well, you may say, well, what about a water heater? Well, a water heater, by code, it tells you that it's to be considered a continuous load. Whether or not your water heater in your house will ever run for 3 hours at its maximum output, regardless of that. And chances are it never will, because if it has 4,500 watt elements in it, there's one in the top and one in the bottom. They usually cycle out. So the maximum output is never both elements on at the same time. It cycles out. However, the National Electrical Code says, you know what? When you're running a branch circuit for that water heater, I want you to take that nameplate as a continuous load. And SISO conductors at 125%. I'm just going to tell you to do it. Then you just do it. You don't read too much into it. You don't say, well, wait a minute, that's not really a continuous. No, the code told you to take it at 125%. So you just do it and you size your conductors accordingly. But what's so important for students is that you're going to get exam questions, or you're going to be real world situations where you may encounter something that is a continuous load. And on an exam, they'll usually tell you that it's a continuous load. And if they tell you it's a continuous load, then hey, ding, 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 then it's a continuous load. So it doesn't matter in your mind whether or not this load is at maximum output. It doesn't matter because they told you it was. So you take it as face value. So let's look at a question example. A classic question is, what size THHN copper conductor do you need for a 40 amp continuous load with 7 current carrying conductors in a EMT, electrical metallic tubing? By the way, EMT is a tubing. It's not a conduit. It is a raceway, but it is not a conduit. I know. I hate being picking on people because all of us can make those little mistakes. I do it all the time, but I do want to get people into the understanding that it's a tubing. It's not a conduit. And why is that important? Because there are specific conduit rules that you can use conduits for certain things that you couldn't use tubing for. So it's important that you understand the difference. And of course, you guys are learning the code. I mean, these are fundamental things that I really want you to take away. Okay. But is it big deal? And probably not. But again, these are just things that I figure I'll throw out there for you. All right, let's start first. Let's do some first things. Now, we know it's a continuous load. So one of the things we haven't looked at in the code is the continuous load or rule for continuous loads and non-continuous loads. So for branch circuits, you're going to be looking at 210.19A1. And for feeders, you're going to be looking at 215.2A1. Now, people say, well, why am I not looking at 225? Because that's something different. That's for outdoor branch circuits and feeders. It's still branch circuits under 210, and it's still feeders under 215. 225 just brings them together and gives you some additional rules for when they're used outdoors. Okay, that's the only difference. So if you have feeder rules in 215 and you have branch circuit rules in 210, then you're looking at it and go, okay, so 210.19A1 says I'm going to take a continuous load and I'm going to do it at 125%. Okay, so we know it's 40 amperes and we call it a continuous load. So I'm going to take those 40 amps, I'm going to multiply that by 1.25. Okay, or if you have a calculator and you do the 125%, my calculator's funky because it's a scientific calculator, so I got to hit all these other damn buttons to do percentages. So I just don't do it. So I go 40 times 1.25. And also, I like to convert all values. For example, 125, you move 2 spaces to the left from the right, and that gives you the 1.25. To move it back to an actual percentage, you move it 2 spaces to the right, that's 125. It's just the way I do it. Same thing with 80%. I start from the right and move it 2 spaces to the left. That's 0.80. That is your decimal. That makes it easier to do your calculations. Get everything down into decimals. It makes the math easier. Okay. So that's how I do it to 1.25. So that's 50 amperes. That's the minimum ampacity required for that conductor so far. Okay. So, you're looking at okay, so I need a conductor that can handle 50 amperes. All right. So, but we're not done. Now, this is one thing that I will talk about that really does screw people's minds up is how it's written in 210.19. And I really do. You're going to learn about this in Derating Demystified, but I really want to focus on it and talk about it real quick. When you look at 210.19A1, you have an A1 and you have an A2. Okay. A1 is when it talks about a continuous load at 125%, and then it says a non-continuous loads at 100%. Yes, you could have a branch circuit, same as with a feeder, that supplies more than just one load, in that collectively you could have a load on that branch circuit that is continuous, and you could also have some other load element that's being supplied that is non-continuous. It's not as cut and dry as this question is, where it was just one load and it was a continuous load. Okay, well, that's easy. So here's what it says under 210.19A1. And again, this is exactly the same under 215.2A1 for feeders. So we'll just focus on branch circuits. It says, number one, A1 says, where a branch circuit supplies continuous loads or any combination of continuous and non-continuous loads, it says the minimum branch circuit conductor size. Okay, so it's not really about the ampacity yet, folks. It's about conductor size, the minimum size that we have to have. It says the minimum branch circuit conductor size shall have an ampacity not less than the non-continuous load, that's at 100%, plus 125% of the continuous load in accordance with 310.15. Okay, now we have an exception for that. Okay, and this is where the assembly, where everything is rated at 100%, and then you don't have to take a continuous load at 125%. You just take it at 100%. That's because all of the components are rated at 100%. That's typically not what you're going to see on standard molded case circuit breakers. They're usually going to be limited to 80%, and 80 is the reciprocal of 125. Okay? So there is an exception for that, but again, unless you get devices, breakers that are rated for 100% that take this into consideration for continuous loading, then the normal thing that you're going to get is going to be limited to the 80%. Okay? All right, so, and again, you're looking for the word 80 in the code, and you're not going to find it because 80 is the reciprocal of 125. And you say, well, what does that mean? Well, what does this reciprocal mean? Well, what it means is if I take the 100 amps, right, and I multiply 100 amps times 0.80, okay, then that would be 80 amps. But if I take 80 amps and I multiply by 1.25, that's 100 amps. So they mean the same. They're reciprocal. But you use them differently depending on what's given to you. If like if they already give me the ampacity of the whatever the load would be, then I can use multiplication and do that times 125%, and then I search for the conductor. And I've already got a conductor that takes into consideration that continuous loading. Whereas if I have a breaker and I want to know what the limit is of the continuous load on this breaker, knowing that breaker is limited to 80%, then I can take the rating of the breaker and multiply that by 0.80, and now I can find out what the ampacity is that I can't exceed that's going to get terminated on that breaker and not exceed the rating of that device, which is limited to 80%. So you understand that's what reciprocal means, okay? So you're never going to see the word 80%, limiting breaker to 80%, but you're going to see the 125. You just need to understand what reciprocal means and what we're talking about here. So don't go hunting for this 80% magic thing in the code. You got to understand how it works, okay? Now, so that is the first one. That's A1. But here's what people forget about. There's also an A2, okay? And A2 says, okay, if all I had was a continuous load, for example, and there was no adjustment or correction involved. In other words, we're in that perfect world, remember? 30 degrees Celsius, 86 degrees Fahrenheit. We don't have more than 3 current conductors. A perfect world. Happy. It's a perfect world. Then I would just stick with this and size that conductor based on 125% for the continuous load and size my conductor accordingly, and I'd be good to go. However, when you do have some type of adjustment or correction involved, like we do in our example, now you have to look at A2. And A2 says, okay, well, the minimum branch circuit conductor size shall have an ampacity not less than the maximum load to be served, okay, after the application of any adjustment or correction factors in accordance with 310.15. So this is after it's served. So what does that mean? Okay. Well, remember what we said? We had a 40 amp continuous load. That may be what the actual load is. It's 40 amps. We're just calling it a continuous load. But the real load is what? 40 amps. I mean, that piece of equipment may have a nameplate. That nameplate may say it's 40 amps. Just because we're telling it to be taken as a continuous load, we're only doing that because of breaker and conductor sizing. The load is still the load, even though it's still 40 amps. And we're sizing a conductor bigger, or we're sizing the breaker based on the limitation, it's still 40 amps. And that's what it means. That's the load to be served. And we have to make sure that the conductor is at least sized to handle that load even after we apply any adjustment or corrections. Now, we learned earlier how to apply those adjustment and corrections, right? But this is saying at the end of the day, the conductor for this branch circuit is going to be at least this size, whether you like it or not. And it's going to be whichever one of these yield the largest outcome of conductor size. So if the conductor size, for example, was based on A1, which is 125%, and you picked a conductor based on this case, we said it was a 50 amps. If you do it based on A2, and you do it based on the adjustment and corrections, if it yields a conductor that's smaller than the 8, then you're still going to go with the 8. Because you have to go with whichever one yields the larger conductor requirement. You with me? Okay. Just want to make sure we understand that. Now, also conversely, if I have a situation where there isn't any continuous loads involved, there's just non-continuous loads, then I might not even have to look at A1 at all because I'm not going to be applying any 125. We're taking the load at the load, which is, again, non-continuous loads at 100%, but yet I still may have to apply 210.19A2 because I do have adjustment and corrections. And I still need to make sure that the conductor size and its subsequent ampacity is equal to or greater, okay, to the maximum load that's being served after I do the adjustment and corrective math. Does that make sense? Hey, folks, I told you this is probably fundamentally one of the hardest aspects for people to understand within the National Electrical Code. It really is. Okay, so let's go back to our question, and I'll reiterate the question again. What size THHN copper conductor do you need for a 40 amp continuous load with 7 current carrying conductors in an EMT? Okay, so we did start first. We said 40 amps times 125%, that's 50 amps. Okay, so we know the amps based on A1. We got it that far. Step 2 was, okay, we had 7 current carrying conductors. So we need to think, what is our multiplier? So we're going to go to table 31015C1, and we'll notice that since we have 7 current carrying conductors, we're going to be at the 70% adjustment factor, okay? Because we have 7 to 9 current carrying conductors. In fact, our question had 7. So we're going to use 70. Now, we want to convert it to decimals. So we go from the right side of the 70 and move it 2 spaces to the left. So now it's 0.70. So that is your multiplier, okay? That would be the multiplier that we're using, okay? Now, we'll do the math. We'll do the math both ways and see what conductor sizes would be here. Okay, so first things first, let's just make it easy for us and just do it the 125% one first and see where we're at with that. So that was going to be a 50 amp. So first thing I would do is just to check this, I would go to a 90-degree C column for THHN, okay? Because it didn't say it was in a wet. It said it was THHN. I'm not going to read any more into this. We're assuming that wet locations and that didn't come into the equation, okay? I'm just going to answer what I've been given. That's it. Just what I got. That's it, okay? Don't overthink it. Don't say, well, it doesn't tell you what the terminals are. Look, this question doesn't even say how it's terminated. So I'm just going to answer the question. It's only asking me the conductor I need for this. Now, in real world reality, the terminals are going to be 75. The conductor's at least 75. So again, in 110.14 A1C, I believe, or A1 or C1A, whatever. If you look in there, you'll see that the option is, look, even if it's under 100 amps, that I can skip the 60 as long as the wire's at least rated 75. If the terminals are rated at least 75, if everything's rated 75, boom, 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 I'm good to go. Okay. Be careful in your exam prep because this is a real world question, but be careful because they're not telling me anything about the terminations. So I'm not going to, I have to be very cognizant of people say, well, God, Paul, which do I use? Okay. Well, in some exams, they may want you to assume that they didn't tell you what the terminals are and you're going to be limited to the 60-degree column, right? You have to be very cognizant of that. Be very, you're going to really have to pay attention to that. But I can't tell you that in a question like that, I can't think for what the test center does. I don't, I can't get into the mind of the people that write the test for every state. But the chances are you have a higher probability of being successful if you don't read more into it than it is. So in this case, I'm not worrying about the terminals. I'm just using what they ask me. That's it. And what I do know is I've got 7 current carrying conductors. I got 40 amps of continuous load, and it's THHN and it's copper. That's it. Just answer what they give you. Okay. For the vast majority of the time, you're going to be okay. I just want to remind you that in the real world, you have other limitations that you need to be very cognizant of. Okay. And that is your limitations in 110.14. based on whatever the temperature limitations and terminal limitations are that you're terminating at. Just keep that in mind, okay? Let that float around in your mind so that you're at least prepared for it, okay? Again, I can't get into the mind of the test taker, so of the person that writes the exam question, whether or not they went that deep or they intended you. There's no standardization for this, so it could go anywhere. Just understand in your mind that those are there, and maybe even look at those options for your answers and see if that is even one of the options. If it's not, then you know they didn't go there, okay? It's the best I can do for you. I'm just trying to give you all of the things to think about here. Okay, but again, this episode is not so much exam prep as real-world scenarios. All right, so if we're doing the math, let's see here. So if I were to go look right now and say, okay, first things first, if I have to pick a conductor that is under the it's going to give me 50 amperes under the 90-degree column, first off, okay, that I need at least 50 amperes. We started out with that. We took the 40 amps at 125%. That's what we started at. We haven't even worked in the 70% adjustment factor yet. So let me get my code book. I'm going to go with you. And I'm going to go down and we're going to go 31016. And we're going to look under the 75-degree column. And let's see here. So I need 50. So it looks like an 8 gauge is good for 55 amps under the 90-degree column. The 10 gauge is not going to work. That's 40. So at least looks like it's 8. And of course, a 6 gauge is good for 75. Okay, so I'm starting there, right? I'll say, okay, at this point, it looks like it could be 8 or 6. But that's just, we haven't even applied any of the adjustment yet. Remember what I said? Just pick your conductor from the 90. I'm trying to make it as simple as possible. Let's move forward. All right, now, let's do that 55 amps under the 8 gauge, and let's do that and multiply that by the modifier of 0.70. And that is 55 amps. You've got your calculator. Do it with me. Times 0.70. That is 38.5. Is that going to work? Absolutely not. Because remember what it said in 210.19a12? That after the adjustment, I still have to handle the load. And what was the load? It was 40 amps. That was the load, right? You with me in this question? So in that scenario, it looks like, okay, well, an 8 would be too small. So what about that 6? Well, the 6 is good for 75 amps. So I take that 75, multiply that by 0.70, and that is good for 52.5 amps. That meets the rule. That's perfectly fine. Now let's double check this again under the 75-degree column. That 6 gauge that we just looked at is good for 65 amps, okay? But we also look under the 8 gauge, and it says 50 amps. But that's been rejected. Why? Because of the adjustment we have to make. Because the conductor falls below that 50 amps. It ends up dropping down to 38.5. So that's not going to work. You see how that works? So even though under the 75 it said it was good for 50, that no longer applies because we had to do an adjustment and correction. And the actual ampacity now of the conductor is reduced below that 50 for the 8 gauge. So it's not going to work for us. Okay. Now, in a perfect world, it would work. If we had no adjustment or corrections, then it may work. But it's not going to work for us now. Okay. Because we're using 210.19a2. Okay. All right. So now, the answer for us is the 6 gauge, okay? Now, let's check that because we did say ours had a continuous load, right? So what if we went the other way and said, well, I want to compare this to taking it at 125% and see what conductor it yields. So watch this. So remember, we're comparing this to 210.19a1 now. We did the A2. We're doing A1. We're going to just use the continuous load and compare and see if that yields a larger conductor. So that would be again, we did it 40 times 1.25. That is 50 amps. Now, we don't use the 90 here because we're not doing adjustment corrections. We use the 75-degree column and we go straight to the 75. So when we did that, we're looking for a 50 amp conductor and that would take us to an 8 gauge. And you're thinking, dude, I can use 8 gauge because A1 says that. Remember, you got to take whichever one yields the larger. So in this case, the 8 under that allowance would not be the larger conductor. When you're comparing A1 versus A2, because I do have some corrections that I have to take place, or adjustments that I have to take place, then guess what? A2 yielded the larger conductor. That's why we went with it. You see how that works? You have to compare A1 to A2 based on what criteria you're given. Okay? Hopefully that makes sense to you. Hopefully it does. Now, that was for the number of conductors. Let's do another little one. What if we wanted to do it based on the ambient temperature? Now, I get it. There's so many of you out there who don't even take ambient into consideration, but we're going to do it today. So let's say you have conductors running through an attic that hits 45 degrees C. Okay, so let's say we're in a raceway. They're running through the attic in a raceway. They're in Chicago and they're running EMT through a raceway, through an attic. Okay, so it hits 45 degrees C in that attic, or 113 degrees Fahrenheit. Well, obviously, the ambient temperature to which that raceway runs through, or tubing in this case, if it was EMT, tubing, but is a raceway, but it's not a conduit. Again, just reiterating that fact, but it's still tubing. It is still a raceway. The ampacity of those conductors are going to change. Now, in this example, we don't have more than 3 current conductors. All we're going to worry about is the ambient. Make our life simple. So we have THHN copper. We have 3 current conductors, so we're well within the 310/16 of the 3 current conductors or less, so we're good there. And it's a 30 amp load. Okay, now, the load didn't say anything about this being continuous load. It just said 30 amp load. That is it. Okay, now, first things first. The load is 30 amps. So I'm going to start with 30 amps. And I need a conductor that's going to be equal to or greater than 30 amps after the correction. Now, did you notice something I didn't do? I didn't go to 210.19A1 because it didn't say anything about it being a continuous load. So the only one that comes into play for me is 210.19A2, because there is going to be an ambient correction that needs to take place here, because I'm going through an ambient temperature that's not 30 degrees Celsius, 86 degrees Fahrenheit. It's elevated. There's heat there. So not only do you have the heat from the attic, but you have the mutual contribution from the heat from the conductors under loading that's going to rapidly get that temperature rising up to the volatility level of that insulation, and it could cause it to melt down. So how do we counteract that? We reduce the amount of current that can go through the conductor to try to keep it from getting to that volatile temperature level of the insulation so it doesn't start breaking down. That's why we do this. Okay, that's why we're playing with these amps, because amps generate heat. Okay, so that's what we're trying to do. Okay, now there's somebody out there to say, well, wait a minute, amps don't generate heat. Resistance is, look, what we're saying it is the more current you pull, okay, is going to generate more heat in a mutual environment under loading. And so we have to do something to reduce that loading. And that's what we're trying to do here. We're certainly not going to reduce the ambient temperature, because that's the attic. It is what it is. Okay. Now, some people ask me and says, Paul, how do you get these values in an attic? It's for an exam, for example, they got to tell you these things. In the real world, it's really hard. But most of the time, I tell people for attics, you can equate, if you're going to have a lot of stuff running through attic and thermal insulation and things like that, then you can add anywhere between 15 to 20 degrees for the temperature or the ambient up there, although it could go much, much higher than that. So there is no, you got to use your own rule. I can't tell you what to use. Attics and different environments. Now, if you're running through a boiler room, for example, then you can get a good baseline of that room. And kind of get an understanding from the engineers, design professionals, with the temperatures liable to be in the room. You can get some extra values on that, but you're just going to have to use your judgment. So on an exam, they're going to tell you because they got to tell you. In the real world, I think the reason most people don't put an ambient correction in is because they don't know. And if it's in the walls in a conditioned space, inside the building envelope and it's an attic that is exhausted or temperature controlled, then none of this would even come into play when it comes to the ambient. But every condition's different, and I just want you to be aware of that. And it does play a role on the conductor's ampacity. Okay. So we started with 30 amperes. I need a conductor that's at least equal to or greater after we do the correction, because that's what it said in 210.19A2. That's what it said. So 30 amps is my load. Now, I need to find the correction factor first here. Let's go on and do that. We'll do this first. So we're going to go to table 31015B1. Now, remember, our insulation is THHN. So we're going to go under the 90-degree column. Again, that's why we're doing it. It's not because of the ambient. It's because of the insulation rating of the conductor that we're using. So in our case, it's 90-degree rated at THHN. So, and we're using since we're talking Celsius, we're going to use the left side Celsius. And we're going under the 90. And since we were talking about 45C, we go down the list here to 45C. And we're looking for the modifier. What is the modifier that we're going to use? And so it's 113 degrees Fahrenheit. So we're going to go down and you'll see that is going to be, 113 degrees Fahrenheit is going to be 0.87. Okay. 0.87 is going to be our modifier for that. Okay. So we write that down. You got your 0.87. Okay. Now let's see. So let's see how we'd apply that. Right. So let's continue. Let's do some work here. Okay. So if I'm dealing with the 90 degrees C, the first thing I need to do, okay, now let's go on. Since I am going to be doing a correction, I now know that I can use the 90 degree for adjustment and corrective purposes on this THHN. So I'm going to go to the ampacity table first. Remember, we got all our numbers now. I'll go 31016. And the reason I'm going to go to 90 because we are making an adjustment and correction. So the code tells me I can do that. Under 31015 says I can do it. So I'm going to go down and I'm looking for the THHN, and I want to see what am I going to be first to make sure that I can handle the 30 amps. All right, so I'm going to go down and let's see here. Okay, so it looks like I've got some options here. Got 30 amps. Okay, it's got to be equal to or greater than 30 amps. Now, you already know without doing anything extra, you should know that if I've got to have a conductor after adjustment and correction that's good for 30 amps, then there's no way that I can start my calculation at 30 amps. So it should be a no-brainer that even though a 12 gauge under the 90-degree column is good for 30 amps, you're certainly not going to start there because you know that you're going to have to make an ambient correction. So whatever you do, it's going to drop below 30. So you shouldn't even waste your time. You know it can't be a 12 gauge. And then we're not even talking about small conductor rules and overcurrent protection. We're just talking calcs here. We're just talking conductor ampacity. But that should be a reason you realize, dude, I don't even need to start there, even though it says 30. Remember, it's got to be 30 amps after the adjustment or correction. Okay, so there's no reason to start there. So logically, you're going to start, if you're going to do the math, you're going to start at the 10 gauge. Which is good for 40 amperes under the 90-degree column. So remember our multiplier is 0.87. So we're going to do multiplication now because we're starting from the 90 ampacity and we're moving down. Okay, so we do 40 times 0.87. Remember, converted into decimals, 87%. Start from the right, move 2 decimal places to the left, 0.87. And that is 34.8 amperes, which is okay. After this ambient correction, do I have a conductor that is okay for use? Okay. At a 30 amp load? Absolutely. What about an 8 gauge? Well, the 8 gauge, you're sitting there going, okay, well, do I need to go any further? Well, obviously, if the 40 amp was good, the 8 is 55 amps under the 90, then you already know that that's okay. It's more than enough. One of the key takeaways that I also want to point out is that you still cannot, even though we got 34.8 amps, if you take 40 amps and multiply that by 0.87, you can't use that 34.8 amps. Okay? I just want to make that clear. You are still stuck to the 75-degree column. You're just doing an adjustment or correction to find out ultimately what the conductor's ampacity is so that you, one, make sure it still has the ampacity you need to handle the load without exceeding the terminal limitations under the 75-degree column. Okay? Because that's what we told you that's what the lugs are. That's what we're using, right? So that's how it works. So now that 10 gauge is now good for 34.8 amps. But if you look underneath the 75-degree column, it says the maximum, it's good for 35 amps. So it's still good, even though after it's only 34.8 amps. We're not using that 34.8 amps, and we're certainly not using that 35 amps. We're just making sure that we have a conductor that can handle the load, right? So we know that 10 gauge can handle the load. Now, I don't even need to do that for the A gauge because that's a no-brainer. Now, how can you quantify this? How can you check this? Well, one of the things you can actually do now is, okay, so now under the 75-degree column for that 10, take that 35 amps that's there and do 35, and now divide that by 0.87, and that gives you 40.20. Drop the 0.20, that's 40 amps, and you just go to the right and you see that equates to the actual 40 degree. For this example, you're just quantifying it, okay? Now, let's kind of look at that. So if I used a 12, for example, because you say it's 30, after that 0.87 is multiplier is added, then it gives us like a 26.1 amps. So that's below. So that's why you can't use a 12, even though you look at it and you say, well, 90 degree, it says it's 30 amps. But no, that's not how it works. Now, one of the last steps, and in this example, we will kick in and show you how we would apply 110.14c. Okay. Now, we're going to check the terminals. Now, we already told you they're 75 degree, okay? But we would do that by going to 110.14c, okay? So when we go there, we must still respect that 75 degree C temperature rating or terminal rating, okay? For typical equipment, 100 amps and under, unless marked otherwise. So if it wasn't marked or didn't have marks, and obviously you didn't know the terminal ratings in the real world, then you're going to be limited to the 60-degree column. And you do exactly the same thing we did. It's just you're going to be limited. You can't exceed the values under the 60-degree column. So in our case, let's just be craps and giggles and say that we were limited by the 60 for whatever reason. And we just determined that we needed a 10. That if you go under the 60-degree column, you'll see that the 10 is good for 30 amps, even under the 60. So the adjustment or correction took place from the 40. After the adjustment or correction, it's still good for 34.8 amps, but the limitation is 30 amps under the 60-degree column. And guess what our load is? Our load was we needed at least 30 amps. So a 10 gauge would still work. Okay, does that make sense? Okay, just wanted to throw that little extra in there for those that say, well, what about if 60 degree applied? And I didn't know what the terminal. In this case, your 10 would still be okay. Okay. So takeaways. A lot of folks will look at the 90-degree column, see the 12 THHN at 30 amps, and think, perfect. That's a 30 amp load, 30 amp wire. I'm good to go, but that would be wrong because of the conditions of use. Okay. And we want to make sure that people understand that when they take all of that away. And that's why it's so important to learn all of these aspects, right? For calculating things, right? Okay, let's look at a couple more because I want to make sure that I cover as much as I can. Let's see. So we have what's called Ampacity traps on exams. Okay, for talking exams, some traps that you might run into. So trap 1, use 90 degrees ampacity for the final answer. You only will use the 90 for the math. When you're selecting a conductor, it's going to be based on the 75 or 60, okay, depending on the limitations, okay? And they typically will tell you the terminal ratings and everything that you need for the question, because I think most boards that write exams or most committees, you might think they're trying to trick you, and not all of them are created equal, but they don't really like ambiguous stuff, right? They try to answer the questions, give you as much information as you can, okay? So just remember that the 90, unless it tells you that the terminals are rated for 90, then you're never going to use the 90 except for adjustment and corrective purposes. The end result, you're going to select a conductor based on 75 or 60-degree column, okay? Trap number 2, forgetting to multiply continuous load at 125%. There's certain areas in the code that tell you to just take it as a continuous load or just to apply 125% just across the board. And then there's other things that they may say in a question that says 40 amps of continuous load. Then you need to know that I take that 40 amps times 125%. Ultimately, remembering that the 40 amps is the actual load. Just because I took the 40 amps at 125%, that's not the new load. That is the value you use for sizing conductors and breakers. That is not the actual load. The actual load was the 40 amps that you started out with. That's an important thing for you to lock in your brain. Just because we call it a continuous load doesn't change the actual load. It is what it is, okay? Trap number 3, okay? Counting equipment grounding conductors as current carrying conductors, they do not count. So when you're counting current carrying conductors and you're trying to apply this adjustment factors, don't count equipment grounds. I know that should sound like a no-brainer, but just don't do it. Also, neutrals. Don't always assume that the neutral is always current carrying. If the neutral only carries the unbalanced current of a multi-wire or a 3-phase system that is balanced, and you don't have a neutral, then you don't count it. Now, if it is a 4-wire, 3-phase Y system with harmonics, things like that, then you're going to, or if you're taking a 2 phases from making a 3-wire system from a 4-wire, 3-phase and creating a single phase, 2-wire, 2-phase with a neutral, then you have neutral current that you have to calculate in, and that would be a current carrying conductor. If you have high levels of nonlinear loads, then you're going to have a current carrying conductor, okay? So typical 3-phase 4-wire Y systems with linear loads, then that neutral is going to count. Don't forget. So read the question. But if it's a neutral and all it's carrying is the unbalanced current from, let's say, a multi-wire branch circuit, then, or a 3-phase delta system, let's say, with a neutral, if you have one, then it's going to be balanced out. Then you might not have a neutral load. So it wouldn't be counted as a current carrying conductor. So important to read the question and understand whether or not you're counting a neutral conductor as a current carrying conductor. It can really throw off your math if they slide one in there, okay? That's something to keep in mind. Another trap that people fall into is doing your adjustment and corrections from the 75-degree column instead of the 90. Now remember, the only time you can do your derating or adjustment and correction from the 90 is when your insulation truly is rated 90 degrees C. Okay? If you're doing an adjustment or correction and you're in an environment which you're using, say, THWN, then that's 75 degrees. So you're going to do your adjustment and corrections from the 75 because of your limitation of the insulation's rating. But if you're in a dry environment and you're using THWN, which is also usually mutually THHN, then in a dry environment, you're going to be doing this from the 90 is where you're going to start your derating. So read the question closely. And again, this is also real world scenarios. Pay attention from where you start your adjustment and corrections from, which can make a big difference, okay? Another trap that you want to steer clear of is if they ask you a question, for example, about non-metallic sheath cable. Now, I can use the 90 degree C ampacity value under 334.80, but ultimately, you're still going to be limited to the 60 degree no matter what. The only reason we're using the 90 is to adjust and correct it to make sure, one, we still have a conductor can handle the load, and as long as that load does not exceed the value that's under the 60 degree column. So we still have a conductor that's equal to or greater than what's under the 60 degree, and the fact that our load does not exceed the 60 degree column's value. That's all we're really doing, okay? So keep that in mind. Don't fall for those little traps, that type of thing. And never use the 90 degree for your end value. In fact, with that one, I always tell people, just go to the 60 right away. Pick the conductor size you need. If it's non-metallic sheath cable, just pick it right away under the 60 degree, and then do the math to make sure you're still okay. Okay? All right. Let's mix a few questions, and let's see if we can answer a few of these questions here. Let me give you one real quick to take away. And you can pause this podcast if you want and work it offline. Let's say I have 55 amps of continuous load is fed through a raceway, and I have 6 current-carrying THHN conductors running through an attic at 40 degrees C, and the terminals are 75 degrees C rated. Okay, what size conductor is required? Okay, so in this case, we know it's 55 amps and it's a continuous load. It tells us that. I don't need to know how long the load runs because the question tells me it's a continuous load. Okay. Now, 55 amps is the actual load, right? I mean, that is the load. But when I see continuous load, that means, okay, I'm going to have to do something. I got to do something else because I got to make sure I've got 55 amps. And because I'm going to have to, because there is a continuous load, I'm now going to have to compare 210.19A1 to 210.19A2. And I'm going to have whichever yields the larger conductor. That's what I'm going to go with. But I also understand that I have a correction and I have an adjustment. I'm going to be honest with you, folks. This is about as complicated as they really do get on an exam. This is a three-step calculation question. And so it's not hard, but you have to think about it in steps. And when I tell you to dissect things, that's exactly what I mean. Okay? So 55 amps, that's my load, period. Write that down. That's your load. 55 amps is a continuous load. Before I even apply any adjustment or corrections, I need to find out what would 210.19A1 be? What conductor would I need first? Okay. And 75 degree terminals, I get all that. It's THHN, I get all that. So 55 times 1.25. And that is 68.75 amperes first. Okay. So if I were to use that first, right, and I would go to the 75 degree column because I'm not using the 90, right, because I'm not doing adjustment or correction. I'm just doing the 210.19A1. I'm just dealing with the continuous load to see what conductor I would need. So in that one, I'm going to look down under the 75 because that's what our terminals are. And remember, don't fall for that. In the real world, if you didn't know what the terminals were, then you would be locked under the 60. But I'm telling you they're 75. Okay. So I'm going under 75 and I'm going to say, okay, I need a conductor that's good for 68.75 amps. So it looks to me that it would be a 4 gauge. Let's see. Yep. Because I need 68.75. The next one, that's 85 amps. So it looks like a 4 gauge. So just write that down. Really, that's all you got to do. Write that down. So 4 gauge copper. Okay. All right. Next, let me go on and find my multipliers. Now, since I've got 6 current carrying conductors, I'm going to go to 31015C1. And it looks like from 4 to 6, it's an 80% multiplier. So I'm going to turn that into decimals. So I'm going to start from the right, move it 2 spaces to the left. So it's 0.80. Okay, I'm writing that down. So that's my multiplier, 0.80. Gotcha. Next, let's get that ambient correction value. Well, we're going to go to table 31015B1. We're going to be in the 90 degree column because it is THHN. And that multiplier, I believe, is 0.91. So let's double check. I did that from memory, but let's go. Never trust it. Go look at it. I'm going to go look at it. So since our temperature is 40 degrees C, we're in the left column. And we're going to find 40 degrees C. There it is right there. And we're going to go to the right. And that is 0.91. So that is correct. We're at 0.91 is my multiplier. Okay, so we've got the 0.91. That's for the ambient correction. And for the adjustment, we've got the 0.80. Boom. Okay. Now, remember what it said? At this point, I already know what I need for the continuous load. I know that a 4 gauge would handle that part, but I need to see if that ends up being the largest conductor. So now I'm going to go using A2. I'm going to say, okay, remember, I'm going to go to the 90. Okay. I'm going to go to the 90-degree column. And I'm going to say, okay, what do I need to do in order to see what size I need for this? Okay, well, let's go to the right. And I'm going to show you a shortcut and a long way to do this and another way to do this, but let's just go this way. So I'm going to say, since I'm starting with the 4 and I know it can't be, it's got to at least be a 4 because that's what the continuous load wants. So I'm going to start with the 4. So I'm going to go to the 4. Okay, and let's go to 310/16. And the reason I went to the 4 gauge is because we already did it for continuous load, and we know that it can't be smaller than a 4 because that was the first one we did for continuous load, so it's got to be at least a 4. We're trying to see if this one requires it to be larger than that. Okay, so I'm going here, and I'm at 310/16. I'm going to go to a 4, and a 4 looks like it's 95 amps. Okay, so I'm going to come back and I go, okay, well, I'm going to do the 95 amps, and I'm going to now do the maths that I had before. I'm going to do it times 8.80 and times 0.91. So I'm going to take that 95, multiply it by 0.80, multiply that by 0.91, and that equals 69.16 amps. Now, the key here is that we knew that the 4 gauge was what's required when it was a continuous load. And all we're doing here is to verify that we still have a conductor after an adjustment or correction that's still going to give us a value that's equal to or greater than what? That was the 55 amps. So obviously 69.16 amps is fine. It's not a problem. Okay. Now you can also do this as well using the 50. Let me show you how you can do this another way. You can actually use the 55 amps, right? That you need to have after the adjustment or correction. So you can do the 55 and do division. Do 55 divided by 0.80 divided by 0.91, and that equals 75.74. So if that's the case, then you go back to the code book under 310/16 and go to 4 again, and look to the right, and you'll see that under the 90, good for 95. Okay, so it's under the 4, it's 95. So it tells you that it's obviously equates and it works backwards and forwards. So whether you start it, and if you were doing it this way and you started at the 55 and you used division, you would be going here and you have to find a conductor that's at least rated for the 75 amps, 75.5. Well, you couldn't go under the 4, right? Because previously it said it couldn't be smaller than, it had at least to be a 4. So you couldn't go to a 6, even though that says 75. But the fact that it is 0.5, you don't drop 0.5. Okay, so it's over 75 amps. So that immediately would push you up into a 4 as well. So that's why you would be at the 95 amp rated conductor under the 90-degree column. So either way, it shows you how to do that. But the reason we started with 4 is because we knew the conductor couldn't be smaller than a 4 because that's what it was in our first equation, 210.19a1. All we're doing now is to validate that and check it now to see if the conductor size changed after adjustment and corrective purposes, because we have to go with whatever the larger is of the two, right? So that's important for people to realize. You have to compare and see how that works, okay? All right, so kind of a wrap up here. Final words, always use the 90 column when you're doing the D rating as long as the insulation of the conductor is rated for that. But always select your final conductor from the 75 or 60 degree, depending on the limitations in 110.14c, or whatever wiring method you're working with, like non-metallic sheath cable. You can use 90, but ultimately you're going to be stuck in a 60. Remember, continuous loads, whether they tell you in a question or you're in the real world and somebody says, hey, this is continuous load, then you're taking that load at 125% for conductor sizing and breaker sizing, but that's not the actual load. The actual load is the value that you're given. Okay, so 40 amps of continuous load is still 40 amps. Yes, you're going to add 125% to it, do it, multiply it by 125% for conductor sizing and for breaker, but if you were asked what the actual load is, it's still the 40 amps. That didn't change. A neutral may or may not be considered a current carrying conductor, depending on what type of system it is. So be very diligent in your questions. In the real world, you'll know that based on the system and what the circuits are. Never, ever apply a temperature correction to the 75-degree column unless you're using a conductor that is rated 75 degrees C in an environment for that, and you'll be using it from the 75 because the insulation's not rated 90. So that's when you would use the 75. But if you're in a dry environment, you're using something like a THHN or a THWN-2. That's what that -2 means, treated as a 90-degree rated insulation. Then you use the 90 to do your adjustment and corrections. So you may use a 75, but it is usually when you're only dealing with an insulation that's rated 75, because you can't use a 90 if the insulation is not rated 90. You understand that? Always follow this order. Determine your load. Find your ampacity under the 90, do your adjustment and corrections, and then validate your temperature ratings by making sure that it doesn't exceed and that your 75 or 60-degree column is going to be enough to handle the load. And so we're always referring back to these 110.14 terminal limitations. And if any of that confuses you, please do me a favor. Go over to Fast Track's Tube and search for derating demystified. Whether it's version 2.0 or 3.0, it's still going to give you those real important factors to remember, because this is probably the most confusing topic for people who are working through the National Electrical Code. And my hope is that I didn't make it more confusing for you. Till next time, folks, stay safe. God bless. We'll catch you in a future podcast.
Thanks for tuning into another electrifying episode of the Master the NEC podcast. We hope you're feeling more powered up and ready to tackle the electrical world with the knowledge and confidence you need to succeed. Remember, in the electrical trade, knowledge is power, and we're here to make sure you stay plugged into the latest insights, tips, and code updates. If you enjoyed today's episode, don't forget to subscribe, leave us a review, and share the podcast with your fellow electricians and industry pros. Until next time, keep your tools sharp, your circuits clear, and your mind focused, because here at the Master the NEC podcast, we're all about sparking your success. Stay safe, stay smart, and keep mastering the trade. From all of us here at Electrical Code Academy, thank you for all your support, and we will see you on the next amazing Master the NEC podcast episode.